Welcome to the second part of Module B training. Module A of this video series provides an introduction to the two fundamental concepts of eco-design: life cycle thinking and environmental assessment. Module B will provide you with a detailed procedure to model the product life cycle and perform an environmental assessment. The second part of Module B will provide you with the basics of life cycle assessment. This video has been developed within the framework of the G.EN.ESI project, which aims to support the integration of eco-design within the design and development process through the development of a methodology and a software platform. The methodology is presented in Module C and the platform and tools in Module D. This research project started in 2012 and involved 8 partners, 3 from academia: University of Bath, University Politecnica del Marche, and Grenoble INP. 1 public institution, the ENEA, National Agency for New Technologies, Energy and Sustainable Economic Development, as well as 4 industrial partners: Granta Design, Cibo Environment, Faber, and Bungley-Fleury-Vectra. It is co-financed by the European Commission. Eco-design is concerned with improving product environmental performance over the life cycle. To assess the current state of your product design in terms of environmental performance, we perform what is called a life cycle assessment. This methodology is standardized by the ISO 40004X series and is divided into 4 steps. The first step is the definition of the goal and scope of your study. The second step is an inventory of all the environmental inputs and outputs of the system under study. And the third step is the assessment of the inputs and outputs regarding the contribution to environmental impact. At any time during these 3 steps, you can interpret the results to apply the interpretation to your application. So the first step of the method is about framing the scope and goal of your study. It is crucial to get the focus right and to define the system and the study properly to have an accurate assessment for decision-making in eco-design. First, you should define the goal of the LCA. In eco-design, it can be to supply environmental information to the design process or to communicate the final performance of your product. A functional unit should be defined. This functional unit is the definition of why your product is used or why the product under study actually exists and what is it used for. I will give you an example of functional units in the next slide. The next stage is to define the system under study. It should include all the elements that contribute to the functional unit for your product. For example, in the case of mobile phone, you should consider all the systems that are used to undertake the following activities: extraction of raw materials, manufacture of materials, components, parts, and the product itself, distribution, the telecom and electricity network used, and the end of life. Once you define the system, you set up the boundary for your analysis. For example, we may decide to disregard the telecom infrastructure in the assessment of the mobile phone. You then define the set of indicators you wish to use, the allocation rules for them. The definition of the functional unit is key to the completion of an LCA. It frames the system under study and provides the ability to undertake valid comparison with alternative design. It is a quantified performance of a product system for use as a reference unit. By doing this, we are not comparing the product but the capacity of different systems to provide a similar outcome to the user. It is defined with an action and a quantification of the intensity of the action. For example, call 1 hour each day for 3 years is a functional unit that can be fulfilled by different systems, such as a fixed landline phone or a mobile phone, or even a computer with a communication app. The exercise at the end of this video will help you understand the concept of functional unit for different systems. After framing the context of your study, you have to record all the input and output that are required for each activity within the life cycle of your functional unit. This is called life cycle inventory. For each inventory, you will define the inputs, such as energy or materials, and all the outputs, such as waste and emissions. Life cycle inventory is a very time-consuming activity. This is why generic system inventories are available in the different software package for life cycle assessment. For example, you may create the inventory for the production of 1 kilogram of ABS, where the inventory represents all the inputs and outputs needed for the production of 1 kilogram of this material. This inventory is called cradle to gate, because it represents the life cycle of ABS from its cradle, being the extraction of crude oil, to the gate of the factory where it is delivered in pellet form. This type of inventory is also used for the production of energy. For manufacturing processes, the inventory are called gate to gate and consider all the inputs and outputs needed to transform the components or semi-finished parts into the finished product. Following the completion of the life cycle inventory, you will have a list of environmental inputs and outputs. To gain a better understanding of the environmental consequences of this input-output list, you can transform them into environmental impacts. The calculation of the environmental impacts is a weighting of the inventory components to illustrate the contribution to an environmental phenomenon. For example, in the assessment of global warming, the environmental impact, you will add the kilogram of CO2 emission identified to the methane emissions multiplied by 25 to give the total impact value. The typical results of a life cycle assessment is the analysis of the contribution of each life cycle phases to different environmental impacts, which can be further broken down into detail. In the figure above, 12 environmental indicators are used. The first one, RMD, is raw material depletion. Then you have energy depletion, followed by water depletion, global warming, ozone depletion, air toxicity, photochemical ozone creation, air acidification, water toxicity, water eutrophication, and hazardous waste production. We can see here the result of the assessment for an electronic product. The use phase is the main contributor to 10 out of 12 indicators. The other two are dominated by the manufacturing phase. This assessment tells us that use phase is a critical life cycle phase, and based on the breakdown of the analysis, that energy consumption during use phase is a significant environmental aspect, an environmental hotspot. This can help direct the redesign effort for eco-design by improving product efficiency in use. We have provided an overview of the key steps required to perform a life cycle assessment. The next video will provide you with detail on the material extraction, production and transfer phases of product life cycle.